folks, so we're coming back today to think about a bit tougher dynamic programming problem. First off, let me introduce you to the problem. We're going to be thinking about the longest common subsequence problem. The idea is you're given two, imagine them as arrays of numbers, and you want to find the longest sequence of characters which appears in both of these guys. Yeah. And, well, let's see if I can find one. Oh, here's one. There's A. There's A. And then there's B. And then there's A. Right? So the sequence ABA appeared in both of these. Right? So ABA is a common subsequence, but it might not be the longest common subsequence. Right? Notice we can skip characters. You can skip characters in either string. So you could have something like, you could instead maybe match the B's here. And then you could skip forward and you could match like, let's say this C against this C, right? Like that. And let's see here. We could do this A, and this B with this B. That would be one, right? So B, C, A, B. Oh, and it's even longer than our previous one. Okay, so both of them have B, C, A, B in them. So you can sit here and you can try and find longest common subsequences between these guys, right? We can sit here and we can just keep trying options. You might ask, can we do better than like 4? Well, you can keep trying some, I don't know, let's say we still did B, but maybe instead of C, we took D, right? Because this is another option. I think the color doesn't show up that well, so let me use a black just to make it a little easier to see. So we could do B and B, D and D, but then we only have 2 characters left here. So this is going to end up being A and B again. So there's another sequence, B, D, A, B, right? So you can fish around and try and see, but I'll go ahead and tell you, there's a bunch of length 4, but there's no length 5. No length 5 exists. And so the goal of our problem is to figure out basically this number, 4, right? 4 is the longest common subsequence between these two strings. And just as a side note here, it sounds like a weird kind of arbitrary problem. It is kind of. I say it's a harder dynamic programming problem, but it's really a stripped down version of the kind of stuff you might do in bioinformatics. Like if you have DNA sequences and you're trying to find similarities between them, this has applications for that. Now, there's other restrictions, biological kind of restrictions that the scientists you work with probably would enforce. But this is really the core of the algorithm, this idea. So this does have applications. This is really useful, even if it's just kind of a stripped down version for the sake of keeping it more readable. Okay? So then how would we solve it? Well, okay, it's a dynamic programming problem. I've already kind of hinted that. But in the meantime, how do we solve it? Like if we didn't know it was a dynamic programming problem, what would be like a brute force algorithm? Brute force, of course, is just a term. It's not a specific kind of algorithm so much as it's usually an algorithm that is definitely correct. Like it's easy to argue for correctness. And it kind of just checks maybe a large set of possibilities or like all possibilities. And, says, oh, well, one of these is definitely the answer. So how would we brute force it? Well, a brute force approach would be thinking something like, let's just check every possible subsequence of X and see if it's also a subsequence of Y, right? Every possible subsequence of X is a subsequence of Y. So I didn't write the code up here. Feel free, if you want to, you can go and write the code. It's a bit messy. But yeah, this algorithm, you can probably guess, is not going to be too great, right? And the reason is because there's a lot of subsequences of X. So we're imagining X is from 1 to M, right? X is from 1 to M index. In that case, how many subsequences are there? This sounds like a tough combinatorics problem or something, but it's actually not that bad. There's a couple ways you could tackle it, but a very quick way to find the answer is to observe that every subsequence will either include or exclude each number, right? Every number kind of has a 1 or a 0, which corresponds to, is it included or excluded? So every number, I say letter, I say number, but really like every letter, every character in your array has a 2 possible states. It's either included in the subsequence or it's not included in a particular subsequence. AKA, you have 2 choices here, 2 choices here, 2 choices here, 2 choices here, all the way down. And so you have 2 to the M possible combinations, essentially permutations of choices. Yeah. So this would give you 2 to the M subsequences of X, right? 2 to the M subsequences exist. Okay, so we can already see the runtime is going to be exponential. I don't think we need to go into too much depth here. Runtime is exponential relative to M. It's actually okay compared to N. If one of the strings was really short and one was really long, this might actually not be a terrible algorithm. The runtime would be something like 2 to the M times, it would either be like the length of this guy or maybe the length of this guy squared, depending on how nice our strategy is, right, for finding if this is a subsequence. But something like this would definitely be sufficient as a brute force approach. We could do it in this amount of time, right? And again, if M is small and N is large, maybe this isn't too bad, but they both could be large. So we need a more general solution. Okay? Of course, this brings us to thinking about what would be a better algorithm. Like, what would a better algorithm look like? Well, we're looking for the length of the longest common subsequence. We actually don't care exactly what the subsequence is for the moment. So maybe we'll focus on that number, right? So we'll later extend the algorithm to actually find the longest common subsequence, or I should say a longest common subsequence, because there can be multiple. We can extend the algorithm to find an actual one. For now, let's just focus on the number that we're trying to find. Okay? I'm going to write this notation to mean length of a string. This is like cardinality of sets, if you've seen that before. But yeah, it looks like an absolute value means length in this context, let's say. And we're going to define a little bit of notation here, a little bit of helpful notation. So I'm going to be thinking about the prefix strings of X and Y. So instead of thinking about every character of X all the way down to M, I'm just going to think about the first I characters, right? From 1 to I. And I'm going to call that the prefix. This is a prefix of x. And same thing with y. We're going to think about y not all the way to n, but just up to some j, right? Okay, so something like that. So we're thinking about prefix, the first j or I characters of the strings. And then we're going to say that Cij is equal to the length of the longest common subsequence between these guys. So this is, again, length, and LCS means longest common subsequence. So this guy denotes, like, how big a common subsequence is there between these two prefix strings. A smaller problem, right? Clearly a smaller problem compared to what we had originally, but our goal is going to be to restate the large problem in terms of these smaller problems. And notice, if I and j are m and n, respectively, then our prefix actually becomes the entire string. And this thing, CMN, will actually be our answer. This will actually be... This is the answer we're looking for. Okay. So there's the clever idea. A little bit of ugly seeming notation. Sorry. Think about it. Pause it. Consider it if you need to, because we're going to be using it. Okay, so then if we're okay with that now, let's think about how to formulate this, how to write this guy recursively. Yeah? Well, Cij is going to depend on something, so don't worry about the proof stuff here. Actually, I'll cover that up, so we're not getting distracted by all the scary stuff down there. But let's just think about how we would define Cij. Well, I claim there's two cases. If x at position I is the same as y at position j, then I can go and recursively calculate ci minus 1, j minus 1, and add one more. So that's one more match. One more match. I'm sorry if that's cut off. It looks like you can see it. That's one more match. On top of however many we get from this. Okay? I think that makes sense, right? If the two characters at the end of the two strings match, right? If I have A, B, C, and if I have X, Y, Z, C, right? If they both end in C, then I can peel off the C's and I can try and match the remaining stuff, right? And I'll add one more match to the best I can do in matching the remaining junk. Unfortunately, otherwise, these two characters don't match. And if they don't match, if you stare at this for a while, you realize we kind of need to get rid of one of the two characters, right? If there's a mismatch at the end of the two strings, right? If the position I and position J characters don't match, then we either need to get rid of the position I character or the position J character. This is where it gets a bit more expensive because we need to consider two cases. We're going to consider first the case, the recursive call, where we get rid of I, we get rid of the last character on X, and then we'll compare that to the case where we get rid of the last character in Y, that is J. And then this max will determine whether it's better to take one character off of the X string or to take one character off the Y string, right? Because one of those characters is not getting matched, right? Absolutely, these two characters can't both be part of a subsequence. Remember, subsequences, they still have to appear in order, right? I can't just rearrange the letters of the strings. I still have to choose them in the same order. So at most one of these guys gets matched. We're choosing which one, in effect. Yeah. Okay. So there's your two cases. Hopefully those make sense. I think we could try and prove these formally. So I have here just to show you could. I do have the proof that this case is correct, that this is really the right option. Now I've omitted the second case, and you can see I've typed up the proof, which is usually a sign that I don't actually want to go into great detail in it. Same here. So you can look over it. It's a proof by contradiction. Essentially, we assume that there was some match. We match the last characters kind of in this strategy you saw here, right? We did the last character match. And we imagine, well, what if that wasn't the right choice? What if there was a better way to match them? And we show that that would be impossible. Okay? So again, I'm not going to drag you through this, but if you're interested, feel free to look at it. We can always talk about it in class or in office hours if you do want to think about how to prove these more formally. But for now, yeah, let's suppose we believe this. We believe that, yeah, these are the only options. You got to do one of those two, and it's really just a game of figuring out which one is better. Now, if you accept that, that's great. There's the recursion. It was really easy to implement, right? Here you go. You're given strings x and y, I and j, right? And you're going to check, are I and j 0? If they are, then there's no matching left to be done, right? If either of them are 0, no characters left. Otherwise, check to see if the last character matches. If they do, then do a recursive call where you strip off one character from both of them and add one to that best match. Yeah, so this LCS, right, this returns an int. It returns the amount of characters matched, just to be clear. So this is the cardinality of the thing, right? Okay, and then the alternative here, you see, is the else case, where we're going to do the max of the two recursive calls. Okay, wow, that's easy. And actually, yes, if you went and coded this up, this would give you the correct answer. Feel free to try. I mean, it's a pretty short program, right? So you can go out and write it. It's a little bit annoying, right? Because you have some string manipulation stuff. But if you just treat them like arrays, you can treat these like array indices, and it shouldn't be too bad, actually. Okay, should be actually pretty much this. Just for good measure, I should mention that LCS, our initial call, always good to think about, well, what do you do initially? Well, our initial call is going to be to LCS. We're going to pass in the two strings x and y, and we're going to pass in originally m and n, right? That's your initial call to the function. Right? And then it works its way down. For example, let's suppose we had the following strings. So if we were trying to match this string against this string. Now, you can look at them as a human being and just see they're not going to match up too well. Like, literally, they have no characters in common. But this is a good example of why this algorithm, even though it will work, it will get you the right answer, it might not be that good. Okay? So what happens when we try and match these two strings here? Well, our initial call is going to be with I equal to 5. So we're looking at the fifth character. We're looking at A. So I equals 5. And J equals 4. So we're looking at the A versus Z. Well, A versus Z, they don't match. So we need to do two recursive calls. Basically deciding, do I get rid of A or do I get rid of Z? Well, since I guess it's written up here, I minus 1 is the first case. Let me do that one over here first. So it's I minus 1 will give me I equal 4, and this will be J equal 4. Right? Still the same J. On the other side, we'll have I still equal 5, but now it'll be J equal to 3, right? Going to that case. And we're going to take the max of those two, right? The max of those two. But, and you probably realized it already, these aren't going to match either. This one is going to be comparing B versus Z. Not going to match. And this one is going to be comparing, it'll be A versus Y. Well, okay, neither of these guys are going to match. So you're going to have two recursive calls. Yeah, it's starting to seem like maybe our original exponential algorithm wasn't that bad, right? You know, try every possibility. Isn't great, but this doesn't seem good either. Let me just put in the possibilities. Let's see, this would be I is decreased, J is unchanged, I is unchanged, J is decreased. And then these guys, again, if you check, we already know nothing matches, so I'm not even going to bother going to the indices. But yeah, if you checked all of these, you're going to find none of these match either. So each of these would produce two recursive calls, and each of these below there would produce two recursive calls. All right? And I think at this point, one of the recursive calls would finally bottom out here. There would be one bottom out, but a lot of these would still keep on going. So they would keep going even below there, until you got down to 0 on one of the strings. So keeps going until you get down to I equals 0 or J equals 0. Which will happen. We're always decreasing by something, but it might take a while. Anything we've done in this last step give you hope that there might be a better approach? Doesn't seem good, right? This doubling doesn't seem good. What you're seeing is like the cost per level in the worst case is going up by an order 2, and you know, it's clearly going up by a factor 2, so it's going to clearly solve to something 2 to some power. That's not good. But before we get into that, there's something that might give you some hope, right? And that's in the repetition. So you can see these cases, these trees right here, are entirely repeated. Every bit of work I do in this tree is the same as the work I do in this tree, right? Literally the same work, you know, just getting repeated. That's a hallmark of dynamic programming. Of course, we already knew we're going to dynamic programming eventually, right? But this is what gives you hope. You're like, oh, there's not that many cases to consider. There's actually only m times n possible cases, give or take, right? Big O, m times n. I guess it could be m1 times n, m plus 1 times n plus 1, or something like that, depending how you count it, if you count the base cases. But yeah, there's only like order m times n cases. And that means our runtime, if we use dynamic programming, should be n times m. So dynamic programming runtime will be this. What does the runtime end up being for this tree? Well, it turns out the height of your tree is determined by basically the worst case is n plus m, right? Because the worst case is you work both of them down in kind of equal measure. So as a quick upper bound for the runtime of this guy, it's like 2 to the power of the lengths of the array. Okay? So clearly not good. Clearly this guy's not that good, especially if we really can do it in n times m time. If we really can do it in like, this is kind of like quadratic time, right? Okay, so let's try that out. Let's see what dynamic programming does for us that this doesn't do. And the one I want to look at is memoization. Memoization turns out to be a bit better in this case. Well, I should say it turns out to be, it has a distinct advantage in this case. Whether it's strictly better or not depends on how you're thinking about the problem. But that aside, yeah, memoization is actually pretty nice in this case for some reasons we'll see on the next table. So memoization, I'll remind you, the idea is we're going to, when we compute a subproblem solution, we store it in a table, and then we check the table before redoing any work. So I'm going to store my results in a table C, and if Cij is null, then I'm going to do that work from the previous page. This is like basically just the code from the previous page. I think I split this off into two cases for some reason. Doesn't matter, right? It's still the same work. It's base cases plus these two recursive calls, which correspond to either match or no match. And then I fill in Cij there, and I'll come down here and return it. Well, if I already had the value, then I skip all this work and I just return it. So I will never redo a computation of a number in the table. Every number in the table is computed once and only once. Yeah? Once, at most once, I should say even. So every number in the table is computed at most once. It turns out sometimes you can even skip numbers. That's where memoization is going to be handy. Okay. So, looking at it, hopefully the code kind of makes sense. You can see I'm creating a table up here. This is just a helper function. Creates a table, sets all the values to null, and then it calls memoization with the same parameters I gave you on the previous page, but also this new table, C. And then it returns CMN, right? Which is where we said our value would be stored. Okay, so let's try it for some very small strings. Let's suppose we had the strings BAB and AB, and we wanted to compare these guys, right? Well, there's only, right, if we think about it, there's only so many kind of comparisons we need to consider. What is this? Four possibilities for how many characters we have left. 0 characters left, 1 character left, 2 characters, 3 characters, right? So this corresponds to what character fills up that position of the string. And this has 3 characters. Again, we have like an empty character, right? So this is no character left. No character left. So let's fill in the table just bottom up. If we have no characters left versus no characters left, this table is going to have the number of matches possible. Well, if both strings were empty, right? If I had not these two strings, but just literally an empty string versus an empty string, no matches would be possible, right? So that's the most basic subproblem. Also, if I had like an empty string versus B, right? Empty string versus B, I'm not getting any matches. Or empty string versus BA, right? Doesn't matter, I'm not getting any matches. So the row and the column, the first row and the first column, are all going to be zeros. This corresponds to the, let me see, I guess it depends. Let's call this J. So this is when J is 0, and this row is when I is 0, right? This is J is 1, J is 2, J is 3. I is 1, I is 2. So yeah, these guys all end up being 0. We can see that because there shouldn't be any matches, and that's also what our algorithm would store in those positions if we were asked to fill them in. Okay. What about further in the table? How many matches can we get for the string B versus A? Right? If I just have the string B versus A, well, still no matches, right? And this isn't a base case, but we look at our two neighbors and we take the max. So we look at the two neighbors and we do the max. Well, the max of our two neighbors is 0, so this will be 0. First interesting case. First kind of interesting case. Let me use the pens to cut them off. So what if we had A, string just consisting of A, versus string just consisting of BA. Well, in this case, this is the last character matches. When the last character matches, it said subtract 1 from I and 1 from J, which means we go up diagonally. We take that number, whatever is there, and we add 1. And yeah, sure enough, we can have one match, right? The string consisting of just A can match one character with the string consisting of BA, right? A versus BA. This is going to be one match possible. What about A, just A, versus BAB? Well, A versus BAB, this is not a match, right? B and A are not a match, but we do the max of the two adjacent elements, and in this case, the max of the two adjacent elements will be 1, right? So see how this is working? So you have the two strings lined up against each other. You're thinking about comparing substrings, but in reality, you only need to look at the two cases, right? You only really need to look at the two cases, assuming it's not a base case. Okay, let's do a couple more here. B versus B. So this is the substring. This is, again, substring A, B versus the string just containing B. Well, we're going to go diagonally top left, add 1, which will mean this is just 1. Then this position, this will be AB versus BA. Not two matches, right? Because we can't reorder elements. We only get one match. And, well, we'll get the max of our two neighbors. Right? Max of top or left. And, well, actually, they're both 1. So this ends up being 1. Okay, easy enough. How about this very last position? This corresponds to the entire string versus the other entire string. And this is, I guess, another interesting one because you can see the last characters do match. So we're going to go diagonally. We're going to add 1 to that number, and the number was 2. Or the number was 1, so this number will be 2 in this corner. And, of course, yeah, that makes sense. There are two, the subsequence here, the longest common subsequence is going to be 2. Specifically, it's going to be AB, is in both of these. AB and AB. Whew. Okay. Hopefully you're clear on that. I have a much bigger table that I'm going to try out on the next page. That's kind of what this memoization algorithm is doing. Again, there's a little bit of a subtle difference that we're going to look at, but it's filling in this table, and then it's getting that number and returning it. And you can see in this case, the amount of work we need to do is essentially the J times I value, right? M times N, give or take an extra column for base cases. Okay. So let's really do the acid test, I guess. This is the case I opened today's lecture with, right? This is the pair of strings that I originally claimed has at most a common subsequence, a longest common subsequence of 4. So if our algorithm is right, it should come up with a longest common subsequence of 4. So let me fill in some easy stuff first. First of all zeros on the first column and the first row, right? Because we're matching nothing against the other string. This, again, think of it as a kind of empty string at this point. Nothing can be done for that match. And then we're just going to follow our algorithm. So I'm going to, when we have to choose the max of two equal numbers, I'm just going to pick the top one. So I'll use red arrows to indicate which one I take the max from. So A and B don't match, so we're going to take the max of our neighbors. The neighbors are the same, so I'm just going to take the top number. Doesn't really matter, right? They're both 0. But here we already have a match. It's B versus B. Cool. So that means we're going to take this number and add 1. Okay. Then we have B and C. Well, B and C, these do not match. But in this case, the max actually, they're not tied. So we do want to take the left as our max. Right? So we propagate that guy. Then we have B versus B. Oh, it's another match. And so we can actually match these guys. And it looks weird because we're not continuing this chain. We're sort of branching off, but that's what the rules say. And we're going to follow the rules. B and D. These guys don't match, so we take the max. In this case, the max is again 1. So we'll take that guy. All right, so the max is indeed should be 1 here. Then we have B versus A. Okay, well, that's still 1. Still 1. And then finally, B versus B. That's a match. So we'll go top left, add 1. Okay. Let's see. D. D versus A, not a match. So doesn't matter which one we take. I'll take the top number because they're the same. B versus D, not a match. Top number in this case is bigger, so I'll propagate from that. D versus C, not a match. I'll take the top number. Right, going a little bit faster now. D versus B, not a match. Take the max. Max is the same either way, so we'll take 1. D versus D. Oh, this one is a match. Get out the blue pen. And it means we're going to add 1 to the diagonal, which means this should be 2. Oh, okay. D versus A, not a match. Take the max. Well, it's going to be our left neighbor. So it's going to be 2. D versus B, not a match. Take our max and be left, right? Feel free to, of course, fast forward if you're confident with what I'm doing, or alternatively pause it and try and fill in the next row yourself and see that that you can follow these same rules, that you're confident with kind of how they work. Okay, C versus A, continuing here. Well, they're same, so we'll just take the top one. C versus B, same, or actually rather max is top, right? So we'll take up arrow again. C versus C actually is a match, so we'll take diagonal up. So I'll be 2. C versus B, not a match, so we'll take the max, which will be 2. C versus D, not a match, we'll take the max. So in this case, again, arbitrary breaking ties, we'll take the top number. C versus A, well, let's see, not a match, and these guys are again same, so we'll take the top number. Okay. And C versus B, not a match, so we'll take the top number. Okay. Next one, A versus A, that actually is a match right away. So we'll take diagonal, so that'll be 1. A versus B, not a match, so we'll break ties, we can break it up. A versus C, not a match, but we'll take top because it's the max. A versus B, not a match, so we'll take top because they're the same, right? Same max. A versus D, also not a match, so we'll take top because max is the same. A versus A, ooh, okay, this is something interesting. A versus A is a match, and so this guy will be 3. Okay. And then we have B versus A, not a match, so we will take left. Okay. Almost there. We have B versus A, not a match, take the max, which will be up. We have B versus B, which is a match, so take the diagonal, add 1. B versus C, not a match, take the max. Tied, so I'll take the top one. B versus B is a match, so actually we will take diagonal, and add 1, which will give us 3. We have B versus D, not a match. And we'll take the max, which in this case is actually the 3 we just got. Ooh, nice. And then we have B versus A, not a match. We've got 3s on either side, so we'll take arbitrarily the top 3. And then we have B versus B, and this one's an interesting one because this one gives us a match, and that gets us to 4. All right. Does that mean we're going to be wrong because we already got to 4? Are we in trouble? Well, let's see. Last row here, A versus A is a match. So I'll add 1. A versus B, not a match. We'll go up. C versus A, not a match. We'll go up. Since they're the same. A versus B, not a match. We'll go up. A versus D, not a match. So we'll take the max, go up. A versus A actually is a match. Oh, we have another one. So this will be 4. Oh, okay. But in that last position, it's not a match. So it actually will end up being 4 in this position because we're just going to take the max of its neighbors. Whew. Okay. There you go. There's your check of our solution from the beginning. Does seem to be correct, right? So the length of the longest common subsequence, equals 4 for these strings. Now, I drew in all those arrows. You might be wondering, why am I juggling all these pens to draw in those arrows? But I drew them in for a reason. And maybe you can guess the reason I wanted to remember that information now. Now, what value do those serve at this point? Well, pause it and think about it if you need to. But the arrows I put in, these are like traceback arrows. So these are like traceback arrows. And by following them, I can actually figure out what matches, what was the actual substring that matched up the characters. So for example, here I have B and B and B. So I got my 4 from here. This arrow points back this way, which means the last character in my match was B. Okay, I go back up to here. Well, this was A and A, so I go up diagonally, following traceback arrows. I want to follow up diagonally, which means the next character is A. Okay, that puts me here. So I have an arrow telling me to go up. Well, I didn't do any matching here, so it doesn't add anything. But then I go up diagonally on D, so that's the next character I matched. And then finally I have B versus B here, which means the final character I matched was B. So it's BDAB. And I gotta dig through all the papers here to find it. BDAB. Yep, that was one of the ones we came up with. Huh. Very cool. And if I use different traceback arrows, if I change the rules, for example, if I'd gone left here, I would have gotten a different match, right? I would have gotten a different match. So those kinds of places where we could make arbitrarily one of 2 choices, those could correspond to different substrings. Yeah. Different maximum length substring, subsequences, excuse me. Not substrings. Different thing. Okay, so that's the traceback arrow mystery solved. But I said there was something about this that would show you the benefits of memoization. How about that one? Have you figured out what would be different with memoization? Because what I just did is really bottom up. I filled in every position. Bottom up fully fills in table. Memoization, on the other hand, well, if you think about it, memoization starts at this position and then looks for what positions it needs to fill in to figure out what goes here. Well, to figure out this position, it needs to know its two neighbors, right? It knows, well, B and A don't match, so I need to know these neighbors. So memoization would calculate them. But then memoization wouldn't bother calculating any of the numbers above here. Memoization would skip all of those numbers and all of these numbers because it doesn't need them. It needs this position of the array and this position of the array. Right? Those guys. So it would choose those next to fill in, right? Those would be the next callback. It needs those numbers to fill in these guys. Okay, well, how do we find those numbers? Well, this one depends on this guy, so we need that one. This one depends on this value, but it also depends on the top value, right? When we have red arrows, we need to look at both our neighbors. Okay, blue arrow, so that depends on this one. Let's see, red arrow, so that depends on both the neighbors, here and here. This one's a blue arrow, so it only depends on this one. Let's see, other ones. This one would depend on this value, right? Because to find this guy, we'd need to go up. This one, let's see, looks like a couple things depend on that. That one would depend on this guy. So we need to find that value. This one would need to find this value. Let's see, this one would need to find this value. Everybody seems to be converging on this guy, so we need that value. We're also going to need this guy's neighbor over here. And by extension, this guy. And this, and this. So all of this top left corner, this is getting filled in. And then down here, let me say there's a couple more, like this guy depends on this value here. And then this one depends on this and this. And then this one depends on this value. And this one depends on this value. Okay, I think I've highlighted, if not all of, at least most of the things the memoization algorithm needs to check. Right? All of these values are ones the algorithm will need to check. Actually, I guess this one will need to check here. Okay. So there you go. These are the ones that memoization checks. So let me write that actually a darker color. And you can see it's like maybe half the numbers. It's over half the numbers, but a lot of these are base cases, right? A lot of them are like the base cases at the end. So it's checking like half as much stuff as the bottom up. And as the table gets really big, it shouldn't surprise you too much to learn that the window where we want to explore, it kind of looks like a diagonal, right? Because we're always trying to match things. So the region of the table we want to calculate actually kind of excludes a lot of the stuff in these two corners. Like this corner and this corner are unlikely to be useful. You know, you could even prove probably some stuff about how many of these values even need to be calculated, like outside of like the absolute worst case, right, where there's no matches, right? These are not going to be used very frequently. And so yeah, consequence, memoization, saves on checks. Fill in less of the table of the table. Okay. I hope that helps to visualize how memoization is different. The recursive aspect of memoization lets it choose to only fill in relevant parts of the table. It gets to skip a bunch of the table that it knows just doesn't matter, right? Okay. Otherwise, yeah, so hopefully that makes sense. This is a tougher example. We'll have a bunch more kind of at this level on the next homework. But this is a good one to kind of open up with, I think. Okay. Just as a side note, right? I mentioned it already, but this LCS turns out to be really important for a bunch of problems. I mentioned the comparing DNA sequences, but turns out it's also used for things like optical character recognition and even things like spell checking. There's variants that are used, right? Trying to figure out what word you might have meant to type has relevance there. Specifically, the thing we're looking for is called edit distance. This is like the amount of changes you need to make to a string to turn it into another string. So this is another kind of extension to this idea that's more directly related to these. Okay. And I'm sure a bunch of other algorithms, of course, that make use of this. And otherwise, I guess that's it. We'll come back next time thinking about, I believe, some graph stuff. Yeah, getting into graph algorithms. Thank you so much, folks.